Greetings to all viewers. This is Professor Ankit Singh. We'll now start with a new module, that is highway materials. Okay, so by now we know that a highway or a road pavement is basically of two types. It might be a bituminous pavement or a rigid pavement. Okay, in a bituminous pavement, the binder used is either bitumen or tar, and in a rigid pavement the binder used is cement. Okay, so in both these types of pavements there are a few layers, okay, in a road. The bottommost layer is the subgrade layer, which is made out of soil, on top of which is subbase course, which is made out of aggregates, that is nothing but stone and dust and soil. It might be a mixture of all these. The base course is made out of aggregates and the surface course is made out of bitumen, which is the binder, or cement and aggregates. Now obviously the aggregates in all these different layers are of different gradations and different sizes. Okay, so let us move ahead with the module. Okay, so what are the things that we'll be studying in this module? Properties and requirements of subgrade soils, HRB classification of soil, determination of CBR of the soil, determination of modulus of subgrade reaction of the soil, properties and requirements of good road aggregates, properties and requirements of bitumen, tar, emulsion and cutback. Okay, so these are a few key highlights or key points that we'll be covering in this module. Okay, pavement materials. Okay, so what are pavement materials? All the materials that are used for the construction of a road pavement are nothing but pavement materials. Okay, so pavements are a conglomeration of materials. These materials, their associated properties and their interactions determine the properties of the resultant pavement. Okay, so pavement is nothing but a conglomeration or a group of different materials. Okay, and what determines the characteristics of the pavement? The properties of these materials and their interactions. Okay, the interaction between any two or more materials. Okay, this will determine the property of the resulting pavement. Thus, a good understanding of these materials, how they are characterized and how they perform, is fundamental to understanding a pavement. Okay, so in order to understand what a pavement is, we need to understand all these properties and the characteristics of different materials that are being used for the construction of a pavement. The materials which are used in the construction of highway are of intense interest to the highway engineer. This requires not only a thorough understanding of the soil and aggregate properties which affect pavement stability and durability, but also the binding materials which may be added to improve these pavement features. Okay, so we need to understand the properties of the materials, okay, used for construction of the pavement. The materials can be soil, aggregate and other binders. Okay, why do we need to study? Because these things affect the pavement stability. Pavement stability is nothing but the pavement strength, okay, or the resistance of the pavement to deformation or deflection, that is nothing but the stability or strength. And durability is resistance to weathering action due to time. Okay, with time everything gets worn out. Okay, so the resistance to weathering due to time is durability. And also the binding materials, the properties of the binding materials are important, okay, because they affect the pavement features. Okay, so the bottommost layer of the road pavement was the subgrade okay, and the subgrade is made out of soil. Okay, so we'll first study the properties of soil or the features of a soil. Soil is an accumulation or deposit of earth material derived naturally from the disintegration of rocks or decay of vegetation that can be excavated readily with power equipment in the field or disintegrated by gentle mechanical means in the laboratory. Okay, so we already know what soil is. It can be either disintegrated rock or it could be decayed vegetation. Okay, and what this soil is excavated using either power equipments, okay, like power shovels, bulldozers and etc., or it can be disintegrated by gentle mechanical means in the laboratory. Okay, so this is how we obtain the soil. It is an integral part of the road pavement structure as it provides the support to the pavement from beneath. Okay, so the subgrade is used in order to provide stability or strength to the pavement from beneath. Okay, since it is the bottommost layer. Okay, and it is the layer which will transfer the load to the earth. Okay, the main function of the subgrade is to give adequate support to the pavement, and for this the subgrade should possess sufficient stability under adverse climatic and loading conditions. Okay, so since the main function of the subgrade is to support the pavement and provide stability or provide strength to the whole pavement, so it should possess sufficient strength, okay, under adverse climatic and loading conditions. Okay, so the climatic conditions could be drastic. Okay, there could be rainy conditions, there could be water stagnation conditions. Okay, even in those conditions the subgrade should be stable, okay, and should be able to transfer the loads to the earth. Now desirable properties. Now these are nothing but the desirable properties of the subgrade soil. Okay, what are the ideal properties of subgrade soil? The properties are stability, incompressibility, permanency of strength, minimum changes in volume and stability under adverse conditions of weather and groundwater, good drainage, and ease of compaction. Okay, so these are a few properties which an ideal soil which is to be used for construction of a subgrade should possess. Okay, so it should provide stability, that is nothing but strength, okay, or resistance to deformation or deflection. Okay, incompressibility, the material should be incompressible. Okay, so the volume should not change or should not get compacted, the volume should not get reduced due to application of load. Okay, permanency of strength, the strength should not decrease with time. Minimum changes in volume and stability under adverse conditions of weather and groundwater. Okay, so there should be minimum changes in volume in the soil in the presence or absence of water or any other weather conditions. Okay, so normally what we observe is in the presence of water the soil gets swelled. Okay, the volume increases, and in the absence of water the soil shrinks. Okay, which results in reduced volume. So these cases should be minimum in our desirable soil. Okay, so the soil should have such properties which lead to least swelling and least shrinkage. Okay, so good drainage. Okay, the water should not be accumulated in that soil. Okay, it should drain off the water as soon as possible. And ease of compaction. Okay, it should be possible to compact the soil easily. So these are a few desirable properties of soil. Next, index properties of soils. Wide The wide range of soil types available as highway construction materials have made it obligatory on the part of the highway engineer to identify and classify the different soils. Okay, since a lot of different types of soils are available, okay, we need some properties or some features in order to differentiate them or classify them. Okay, so index properties are one of those properties which help us to classify the soils. The soil properties on which their identification and classification are based is known as index properties. Okay. The index properties which are usually used are grain size distribution, liquid limit, shrinkage limit, and plasticity index. Okay. So although you will be studying all these properties on soils in detail in your geotechnical engineering 1, that is module 1 in that, so I'll just be going briefly on all these topics. I won't be explaining them in detail here. Okay, so among all these 4 index properties, the first one is grain size analysis. Okay, so what do we basically do in grain size analysis? We observe the size of each grain in a soil and then classify them based on the grain size. Okay, soils with higher grain size and soils with lower grain size, okay, we classify them using their size of grains. The grain size distribution is found by mechanical analysis. The components of soils which are coarse grained may be analyzed by sieve analysis and the soil fines by sedimentation analysis. Okay, so there are 2 types of analysis that we carry out on any type of soil. Okay, for coarse grained soils what we do is we do sieve analysis, and for fine grained soils we do sedimentation analysis. It therefore carried out to determine the percentage of individual grain size present in a soil sample. Okay, so we carry out the the grain size analysis to find out the size of grains present in the soil sample. The sieve analysis is a simple test consisting of sieving of a measured quantity of the material through successively smaller sieves. The weight retained on each sieve is expressed as the percentage of the total weight of the sample. Okay, so what we do is we arrange a set of sieves. Okay, we form a vertical column of the sieves with the highest sieve at the top and decreasing the size as we go down. Okay, so the bottommost sieve, which is just above the pan, would be of the least size. Okay, so what we do is we put the weighed sample of aggregate through the topmost sieve, and later on we calculate the size on each sieve divided by the total weight of the sample. Okay, so by this we will get the proportion of different grain sizes present in our soil sample. Okay, this is nothing but sieve analysis. The second one is sedimentation analysis. In case of the sedimentation principle, the larger grains in a suspension settle faster and is used for finding out the grain size distribution of fine soil fraction passing 75 micron sieve. Okay, so anything that is retained on a 75 micron sieve, what we do is we carry out sieve analysis with that soil, but all the soil which passes through the 75 micron sieve will be tested using sedimentation analysis. Here what is the principle that is being used? The principle is that the larger grains, okay, which are under a suspension in water will settle down at the bottom of the container, faster as compared to the finer sized grains. Okay, so this is the concept that is being used. Okay, next, consistency limits and indices. Okay, the physical properties of fine grained soils, especially of clays, differ very much at different water contents. Okay, so water will behave differently according to its water content. Sorry, any soil will behave differently based on its water content. Okay, what is water content? It's nothing but the amount of water which is present in the soil sample. Okay, so if the soil sample has more water content, then it behaves like a liquid or a semi-liquid. Okay, and as the water content reduces, it behaves plastically. Okay, it behaves like a plastic material, it deforms shape, and similarly as the water content keeps on reducing, then the soil behaves like a solid object. Okay, like a brittle object. So what we do is, based on this water content, we establish a few limits. Okay, these are nothing but the consistency limits. Okay, a clay may be almost in liquid state, or it may show plastic behavior, or may be stiff depending on the moisture content. Okay, this is what I just explained. Plasticity is a property of clay soil which is the ability to undergo changes of shape without rupture. Okay, so what is plasticity? It is the property of a clay soil to undergo changes in shape without any rupture. Okay, without any cracking or breaking. Okay, Atterberg in 1911 proposed a series of tests for the determination of the consistency and plastic properties of fine soils. These are known as Atterberg limits and indices. Okay, so Atterberg proposed a few series of tests to be carried out on soils, okay, to determine their consistency and plastic properties based on water content. So these limits or tests are nothing but they are known as the Atterberg limits. So Atterberg limits are nothing but liquid limit, plastic limit, and shrinkage limit. Now what is liquid limit? It is defined as the minimum water content at which the soil will flow under the application of very small shearing force. Okay, so it is nothing but the minimum water content that is present in the soil sample, due to which the soil will act like a liquid and it will flow. Okay, on application of a under the application of very small shearing force. Okay, plastic limit. It is defined as the minimum moisture content at which the soil remains in a plastic state. Okay, under this minimum moisture content or water content in a soil, the soil will remain or act as a plastic material. Okay, and we already know what a plastic material is, or what is plasticity: the ability to deform without any rupture. Okay, next we look at plasticity index later on. First we'll see shrinkage limit. It is defined as the maximum moisture content at which further reduction in water content does not cause reduction in volume. Okay, it is the lowest water content that can occur in clay soil sample which is completely saturated. Okay, so what is shrinkage limit? It is the maximum water content, okay, which is present in a soil sample, under which if any water content is lowered, okay, or any water is being taken out from that sample, then there would be no reduction in volume, or there would be no shrinking. Okay, normally what happens is, when we remove water from a soil sample, there is a shrinking which is observed. Okay, the volume reduces, but What is shrinkage limit? It is that water content at which if there is any reduction in water content, there will be no reduction in volume. Okay. Now, what is plasticity index? It is defined as the numerical difference between the liquid limit and the plastic limit. Okay, so it is nothing but the difference between liquid limit and the plastic limit. Plasticity index thus indicates the range of moisture content over which the soil is in plastic condition. Okay, so from the liquid limit percentage of water content to the plastic limit percentage of water content, the soil will remain in a plastic state. Okay, so that is nothing but the difference between these two limits, and that is known as plasticity index. So the next topic is soil classification systems. I'll start with this in my next lecture. Thank you.